All right, we're in Helicopter Flying Handbook. This is chapter 11, page 8 of 24, height velocity diagram. All right, the height velocity diagram, or HV curve, is a graph charting the safe, unsafe flight profiles relevant to specific helicopters. As operation outside the safe area of the chart can be fatal in the event of a power or driveline failure, it is sometimes referred to as the dead man's curve by helicopter pilots. By carefully studying the height velocity diagram, a pilot is able to avoid the combinations of altitude and airspeed that may not allow sufficient time or altitude to enter a stabilized autorotative descent. The pilot may want to refer to this diagram during the remainder of the discussion on the height velocity diagram. All right. In the simplest explanation, the height velocity curve is a diagram in which the shaded area should be avoided, as the pilot may be unable to complete an autorotation landing without damage. The HV curve usually contains a takeoff profile where the diagram can be traversed from zero height to zero speed to cruise without entering the shaded areas or within minimum exposure to shaded areas. The portion in the upper left of this diagram demonstrates a flight profile that probably does not allow the pilot to complete an autorotation successfully, primarily due to having insufficient airspeed to enter an autorotative profile in time to avoid a crash. The shaded area on the lower right is dangerous due to the airspeed and proximity to the ground, resulting in dramatically reduced reaction time for the pilot in the case of mechanical failure or other in-flight emergencies. The shaded area at the lower right is not portrayed in HV curves for multi-engine helicopters capable of safely hovering and flying with a single engine failure. The following examples further illustrate the relevance of the HV curve to the single-engine helicopter. At low heights with airspeed such as hover taxi, the pilot can simply use potential energy from a rotor system to cushion the landing with collective converting rotational inertia to lift. The aircraft is in a safe part of the HV curve. At the extreme end of the scale, 3-foot hover taxi at walking pace, even a complete failure to recognize the power loss resulting in an uncushioned landing would probably be survivable. As the airspeed increases, without an increase in height, there comes a point at which the pilot's reaction time would be insufficient to react with a flare in time to prevent a high speed and thus probably fatal ground impact. Another thing to consider is the length of the tail boom and the response time of the helicopter flight controls at slow airspeeds and low altitudes. Even small increases in height give the pilot much greater time to react. Therefore, the bottom right part of the HV curve is usually a shallow gradient. If airspeed is above ideal autorotation speed, the pilot's instinct is usually to flare to convert speed to height and increase rotor RPM through coning, which also immediately gets them out of the dead man's curve. Conversely, an increase in height without a corresponding increase in airspeed puts the aircraft above a survivable cushion in height impact and eventually above a height where rotor inertia can be converted to sufficient lift to enable a survivable landing. This occurs abruptly with airspeeds much below the ideal autorotative speed, typically 40 to 80 knots. The pilot must have enough time to accelerate autorotational speed in order to autorotate successfully. This directly relates to the requirement for height. Above a certain height, the pilot can achieve autorotation speed even from a 0-knot start, thus putting the OGE hovers outside the curve. The typical safe takeoff profile involves initiation of forward flight from 2 to 3 feet, landing gear height, only gaining altitude as the helicopter accelerates through the transitional lift and airspeed approaches a safe autorotative speed. At this point, some of the increased thrust available may be used to attain safe climb airspeed and will keep the helicopter out of the shaded or hatched areas of the HV diagram. Although helicopters are not restricted from the conducting maneuvers that will place them in the shaded areas of the HV chart, it is important for pilots to understand that operation in those shaded areas exposes pilot, aircraft, and passengers to a certain hazard should the engine or driveline malfunction. The pilot should always evaluate the risk of the maneuver versus the operational value. So we'll go into the effect of weight versus density altitude. The height velocity diagram 11-3 depicts altitude and airspeed situations from which a successful auto-rotation can be made, the time required and therefore altitude necessary to attain a steady state auto-rotative descent is dependent on the weight of the helicopter and the density altitude. For this reason, the HV diagram is valid only when the helicopter is operating in accordance with the gross weight versus density altitude chart. If published, this chart is found in the RFM for a particular helicopter, figure 11-4. The gross weight versus density altitude chart is not intended to provide restrictions to gross weight, but to be an advisory of the auto-rotative capability of the helicopter during takeoff and climb. A pilot must realize, however, that at gross weights above the recommended by the gross weight versus density altitude chart, the values are unknown. Assuming a density altitude of 5,500 feet, the height velocity diagram, figure 11.3, would be valid up to a gross weight at approximately 1,700 pounds. This is found by entering the graph in figure 11-4 at a density altitude 5,500 feet, point A, then moving horizontally to the solid line, point B, moving vertically to the bottom of the graph, point C, with existing density altitude, the maximum gross weight under which the height velocity diagram is applicable, 1,700 pounds. Charts and diagrams for helicopters set out in Title 14 of the Code of Federal Regulations 14 CFR Part 27, Airworthiness Standards, Normal Category Rotary Aircraft, are advisory in nature and not regulatory. However, these charts do establish the safe parameters in operation. It is important to remember these guidelines establish the tested capabilities of the helicopter. Unless the pilot in command pick is certified test pilot, operating a helicopter beyond its established capabilities can be considered careless and reckless operation, especially if this action results in death and injury. Common errors. Performing hovers higher than performed during training for hovering auto rotations and practice proficiency. Excessive nose-low takeoffs. The forward landing gear would impact before the pilot could assume a landing altitude. Adding too much power for takeoff. Not maintaining landing gear alignment with takeoff path until transitioning to a crab heading to account for winds. All right, so we'll hold off there. That went into the effect of weight versus density altitude, and we went over the height velocity diagram, page 8 and 9 of 24 in chapter 11. See ya. Ooh.